Okay, so hello and welcome once again to Principles of Reinforced Concrete. And in today's video, I will be showing you on how we would be solving for the design strength VPN of a certain axial member under uniaxial bending using interaction diagram. So in the previous video, we have solved for the value of VPN using the analytical method. And in the analytical method, so this was to be the steps that we have done the last video. So in this problem, for us to solve for it via analytical method, you must of course draw its stress diagram and analyze it as a beam while assuming for the value of RC. What we did here was that we have assumed for the value for your C. Where was that? We have assumed for the value of C and resolved all of the parameters up until a certain equation was already satisfied. Mn must be equal to P and E. So up until this equation was satisfied, or let's say that your C assumed is to be equal to C actual. So that is from the analytical method. Okay, once again, we wouldn't be making use of that method any longer because, of course, we would be making use of an interaction diagram this time. So what is to be an interaction diagram in the first place? So this one right here is to be one example of an interaction diagram. So an interaction diagram, for starters, is to be a graphical representation of the compressive strength of a certain member versus its moment capacity, given, of course, the axial load. Okay, so anyway, guys, so if this is to be your axial load P, and this is to be your moment, this is now to be its behavior. Okay, so for example, that for our certain section, it is to be concentrically loaded. So when we say concentrically loaded, it wouldn't be having any moment. So what that means is that its moment is now to be equal to 0. So meaning, guys, that this is now to be its nominal strength Pn. So once again, this is to be for concentrically loaded columns because it does not have any moment. But if we would be introducing a certain moment, of course, its Pn, or let's say its nominal axial strength, would now be decreased. So bababa siya because, of course, it is not concentrically loaded anymore. Okay, so with that, so for every increase of your moment, your Pn would now be decreasing up until, let's say, the balance condition. So after the balance condition, even though that we will now be decreasing its moment, its Pn, or its strength in axial, would also decrease. Okay, so this is already familiar with you guys. So this is now to be your balance condition. And your balance condition is to be a condition wherein the strain of your tensile steel is to be equal to the strain if it is to be yielding. So if you can remember, guys, so your Fs is to be exactly equal to your Fy. So in this condition, this is now to be your balanced condition. So if Fs is to be less than Fy, so it is now to be compression controlled. And let's say that if your Fs is to be greater than your Fy, it is now to be tension controlled. But if this governs, your Fs should be equal to Fy because your Fs cannot go beyond your Fy. Okay, so with that, guys, so if we are to solve for the Pn using our interaction diagram, this method is to be a graphical method. So basically, we will be checking for a graph. So let us have an example here. So in here, guys, so these are to be the interaction diagrams that we will be making use for our example, no? Okay, so these interaction diagrams here are only used for academic purposes. So according to the author, Arthur Nielsen, these interaction values here must only be used for instructional purposes. So if you want to make use of an interaction diagram that is accurate, so better if you would be making use of a computer program, or if you can, let's say, produce an interaction diagram that is to be accurate. So ayun. Okay, so once again, these are to be the interaction diagrams, and as you can see, we have plenty of interaction diagrams that we can use here. So for a moment. So we have this interaction diagram, and etc. Okay, so the limitation of using an interaction diagram is that for you to, of course, make use of it, you must, of course, take note of these following conditions. So in this case, guys, as you can see, you can only make use of this interaction diagram if your f prime c is to be equal to 4 ksi and your fy is to be equal to 60 ksi. So what we will be doing here is that we will be converting this into megapascals first. So for our conversion factor, 1 ksi is to be equal to 6.895 megapascal. So looking at the calculator, so let us convert this. So 4 times 6.895. So that is to be exactly equal to 27.58 megapascal. So 27.58 megapascal. And as for our Fy, so just multiply it once again. So 60 times 6.895. So that is basically equal to 413.7. So 413.7 megapascal. Okay, so as you can see in the problem, which is to be which is to be below me, our F prime C is to be 27.58 megapascal and our Fy is to be 413.7 megapascal. And as you can see, it is to be exactly 413.7 and 27.58. So sinadya ko yan guys para eksakto tayo. But for example guys, that your F prime C is to be equal to 28 megapascal and your Fy is to be 414 megapascal. The question is, can you use this interaction diagram? You can use it, but take note that it would be having a slight error because of rounding off of numbers. So if you have an interaction diagram that has exactly the parameters for your problem, better make use of those. Okay, so guys, as you can see in this, so for our F prime C, this is already satisfied, and our Fy, this was already satisfied. But what about for our value for sigma? So let us solve for that later, no? So we will be solving for the value of sigma if we would be solving for this. I mean, if we would be making use of this interaction diagram here. Okay, so another parameter that you must take into consideration first, or another criteria for you to make use of this interaction diagram, is that your section must look like this. So what I mean here is that you can make use of this interaction diagram if you would be having your steel rebars here at this portion and steel rebars here at this portion which are equally spaced. Okay, so for example guys, that you have a certain column that is, let's say, still a rectangular column, but let's say that it would only have one layer here, then you might as well make use of this parameter or this interaction diagram here. And let's say that you would be having a certain section that is circular, then make use of these interaction diagrams here, depending once again upon the value for your gamma. So your gamma here, so gamma 0.6. So check nyo kung yung gamma niya 0.6 and etc. Okay, so with that guys, let us go back to our whiteboard and let us now check for the parameters. Okay. The first thing that we will be solving for here is to be the value for your gamma h. So for your gamma h, for your gamma, I should say. So gamma. So what is to be the value for your gamma? So this one here is to be an example of the interaction diagram that I have shown you a while ago. So I will just be increasing this. So this is just to be an example. And as you can see, for the value for your gamma h, that is to be the distance from this point up until this point. So that is once again for your gamma h and not gamma. Okay, so in this case, guys, this is now to be the value for your gamma h. So if the whole h here, so if this is now to be equal to, so 650 mm. So 650 mm. And this one here is to be, let's say, 400 mm, which is to be given by the problem. And the distance from the concrete to the centroid of the longitudinal bars is to be 65 mm. So what that means is that this is now to be equal to 65 mm up until the centroid. So for your gamma h, so I will just be writing them here first. So gamma h, this is to be equal to 650 millimeters minus So the concrete cover here and the concrete cover here, or the effective concrete cover. So minus 65 mm, minus 65 mm, which accounts for both the right and the left side. So with that, our gamma H is now to be equal to, so looking at the calculator, so 650 minus 65 minus 65, and that is now to be equal to 520. 520 mm. But take note, guys, that this is to be your gamma H. So gamma is now to be equal to gamma H divided by H for H to cancel out. So with that, guys, so for your gamma, that is now to be equal to 520 mm divided by what is to be the value for your H? 650 mm. So 650 mm. So side note, guys, so disclaimer and a side note that for the value of H here, it does not automatically mean that it is to be the value of H here. The value of H here is to be the distance, the section property of course, your section that is to be along the direction of your eccentricity. So in this case, guys, your eccentricity is to be here. So for eccentricity, which is to be 312, this is now to be 312. So this is 312. So for the value for your H, that should be this dimension. However, guys, so for example, that your eccentricity is to be along this direction. So let's say that this is now to be your load. So if that is now to be your direction, the value for your H should be 400. So do not get confused here, guys. So it is not automatically the case that your H is to be equal to 650. So once again, it would depend upon the location of your load and the direction of your eccentricity. But once again, the direction of your eccentricity is to be along this direction. Thus, 650. Okay, so with that, guys, the value for our gamma is now to be equal to, so 520 divided by 650, and that is to be exactly 0.8. So 0.80. Okay, so with that, guys, so we will now be searching for what is to be applicable to our section. So here. Okay, so let's go from the top. Okay, so can we make use of this one right here? So can we make use of this interaction diagram? So short answer, no, because the gamma here is to be equal to 0.6 and our gamma is to be equal to 0.8. So let us scroll down up until this point. Okay, so with that, guys, we will be making use of this interaction diagram because the gamma here is to be exactly 0.8. But for example, guys, that the gamma that you have solved is, let's say, 0.78, just for example. So you can see we do not have a 0.78 gamma here in the interaction diagram, but if you have, better. But if not, you can actually get the result here at this table, at this diagram, and get the result at this diagram. Then after getting the answer, so you will now be making use of ratio and proportion. So what I mean here is that, for example, that your gamma is to be equal to 0.78. So get your answer with a gamma of 0.8 and a gamma of 0.7. So using ratio and proportion, get the answer here. Okay, so with that, guys, we will now be making use of this particular interaction diagram here because our f prime c is to be equal to 4 ksi, our fy is to be exactly 60 ksi, our sigma is to be equal to 0.8, and our section actually looks like this and not the other sections. So if I would be scrolling down, hindi naman ganito yung itsura ng section natin, hindi naman ganito. And with that, guys, we will be making use of this particular interaction diagram. Okay, so how can we make use of this interaction diagram, guys? So, by the way, I will just be zooming in for a moment. Okay, guys, so as you can see, we have this part here. So we have this part here and this part here. So this one on your left is to be the value for your Kn, and the portion at the bottom part is to be the value for your Rn. So we can actually make use of either of them for us to solve for the value of our Pn. So guys, if I am to zoom in here, so as you can see, whatever the value is here, so as you can see, meron kayong value dito sa part na ito. So by the way, my calculator is blocking the way. So you have here your Kn is equal to Pn divided by F prime C times Eg. So you can solve for your Pn here. So these are to be the values for your Kn. And if you want to make use of the values here at the bottom part, you can also, well, make use of it. So your answer should be the same. Okay, so what are to be the parameters that we should know? So as you can see, guys, we have here the value for your E divided by H. And you also have here the value of your rho G. So what we will be doing here is that, let's say that the ratio of your E divided by H is to be 0.1. So we would be making use of this particular line. Then we will now be checking the cross-sectional steel ratio of your section. For example, that your cross-sectional steel ratio is to be 0.5. So what this means is that you will be making use of this particular curve. Okay. So with that, guys, if this is now to be its intersection, what you will be doing is that you will be projecting it to the left or projecting it downwards. And if you would be projecting it to the left, guys, if you would be projecting it here, so get the value of your Kn here. Then, using your Kn, you can now solve for it. You can now solve for Pn using this equation. So, cross-multiplying. So, if you are solving for the value for your Pu, then make use of this. But for our lesson, let us just make use of this. Though mas mabilis, it would be faster if you would be making use of this equation. But theoretically speaking, I think you would be understanding it better if you would be making use of this equation. But your answer should practically be the same. Okay, so going back to our whiteboard. Okay, so for a moment. Okay, so as you can remember, guys, that we will be making use of E divided by H and for our rho G. So for the E divided by H, so I will just be erasing all of this. So this is not to be our gamma H. And what about for our E divided by H? So direct substitution. So our E is to be equal to 312. So 312 millimeters. So 312 mm divided by H, and our H is to be 650 mm. So 650 mm. So with that, our E over H value is now to be equal to, so 312 divided by 650. So this is now to be equal to 0.48. Okay, so with that, guys, so if we will be making use of 0.48, this is now to be the line for your 0.4, and this is now to be the line for your 0.5. So 0.48 is to be exactly at this part, guys. So this is now to be our 0.48 line, because this is now to be 0.4, this is now 0.42, 44, 46, and 48. So once again, we would be making use of this particular line here. But what curve should we use? So your curve, guys, is to be dependent upon your rho G. So your rho G, So for your rho G, guys, I would just be drawing in blue. Writing in blue. So for your rho G, this is basically the gross sectional steel ratio. So that is now to be equal to the area of the steel divided by the gross sectional area. So for the area of the steel, so hindi na ipakita dito. I have forgot to include here the diameter of the rebars. But for the rebars, let us use diameter 28 millimeters. And we have, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pieces of diameter 28 mm rebars. Okay, so with that, this is now to be equal to, so pi over 4 times 28 squared times the number of pieces, which is to be 12 pieces. So times 12 divided by the cross-sectional area, and that is now to be equal to 400 times 650 mm. Okay, so with that, our rho g is now to be equal to, so looking at the calculator, so pi divided by, pi divided by 4 times 28 squared times 12 divided by 400 times 650, and our answer here is to be 0.028. Okay, so this is now to be our rho g. So in here, guys, so we have a rho g for 0.02. So basically, guys, this is to be the line for 0.02, or I mean the curve point for 0.02. And this is now to be the line for 0.03. Okay, so with that, guys, what we will be doing is that we will be getting the fraction here, which is to be 80%, because as you can see in the calculator, 0.028. So it is approximately in this location. So guys, once again, this is one limitation of our interaction diagram. Because it is graphical, you would be approximating, especially for fractional parts. So I am assuming that for my rho g, it would approximately be here, because once again, this line, this curve here is to be for your 0.03, and this curve here is to be for your 0.02. So once again, I am assuming that your 0.028 is to be exactly here. So with that, after pinpointing the location of the intersection of your E over H and your rho g, you will now either be projecting it to the left or projecting it downwards. So in here, guys, so I am assuming that my projection is correct. So let's say that this is to be it. So as you can see, the value for my Kn here is to be equal to 0.5. So what that means is that, guys, for Kn be equal to 0.5, so 0.5 is to be equal to Pn divided by F prime C times Ag. So with that, guys, substituting known values, so 0.5 here is now to be equal to Pn divided by F prime C. So our F prime C is now to be equal to, so by the way, guys, it is better, I think, if I would be writing here. So dito ko na lang isulat. So I would just be deleting this first. So lagay natin dito. So lagay din natin ito dito sa taas. Then, okay, from the diagram, so Kn is to be equal to Pn divided by F prime C times Ag. So substituting known values, so Kn is now to be equal to 0.5. This is to be equal to Pn divided by F prime C, and that is to be 27.58, times the cross-sectional area, and our cross-sectional area here is to be 400 times 650. Okay, so with that, cross-multiplying, the value for our Pn is now to be equal to, so 0.5 times 27.58 times 400 times 650. So that is now to be equal to 3585400 newtons. So with that, if you want to convert this into kilonewtons, just divide this by 1000. So divided by 1000. So what that means is that our Pn is to be equal to 3585.4 kilonewtons. So there. However, guys, the question here is to be what is to be the design axial strength. So for the design axial strength, guys, that should be phi Pn. So if this is now to be your Pn, so for the value for your phi Pn, considering that phi is to be equal to, so this is now to be a laterally tied since this is to be a square. So by default, unless otherwise specified, this is to be a tied column. So our phi is to be equal to 0.65. So once again, for tied columns. Okay, so with that, our PU or our phi Pn, this is now to be equal to, so 0.65 times 3585.4. So this is now to be equal to 2330.51 kilonewton. So this is now to be our final answer.